Alright, so let's start. Let's solve the problem 3 in this assignment, and it is to find the displacement current between the plate of a capacitor with area of A and the separation of D, which voltage vary by time V equal to A times T square. So I have to first explain what is the displacement current. The displacement current is a current produced by the rate of change of the electric displacement field. It's different than the conduction current in the way there is no actual movement of electron. Okay, and now I'm going to write a simple circuit involving the capacitor. Okay, so this one is the capacitor. So normally there is a conduction current in the wires, right? But at here between the capacitor plate, there is no conduction current. There is instead the displacement current. So we derive how can we find displacement current? So as the definition, the current is the rate of change of charge by time, and the charge is equal to capacitance times the voltage difference, right? And the capacitance is the epsilon times by the surface area divided by the distance between the plate, and the voltage difference is the electric field times the distance. So you can see that the distance can be cancelled, and then as you know that the electric field times the area is the electric flux, right? So now we have the final equation of the displacement current, which is epsilon times the change of the electric flux over time. So this is the displacement current. So let's use it with our equation. So for displacement current is equal to the epsilon times the electric flux, right? And it states that the voltage is vary, right? So electric flux is equal to area times electric field. This one, and the area is that's simply A. And the electric field is the voltage difference divided by the distance between the plate, right? So this is the voltage difference divided by the distance over time. And then it's that voltage equal to A times T square. So we just simply this one, and just use simple calculus, and we will get the equation in this equation of the displacement current between the plate. This one is the displacement current. We have figured it out. So thank you for your listening. Let's move to the next question.
Hello, my name is Apiwit. So for this question, number 1, the accompanying figure shows two situations: an electric field vector E and an induced magnetic field line B. Which statement is correct? And there are 4 choices. So first of all, you need to know this formula. Integral B ds equal to mu 0 I enclosed equal to mu 0 epsilon 0 and the flux by dt. And first of all, let me see the figure 8, this thing. And from the right hand rule, so this thing, so if B is counterclockwise, the direction of I or the current will point up or will be upward. So we would know that I direction will be upward. And from this formula, the direction of I is the same direction as the flux, but in this question A is constant, so we would imply that the direction of I is the same direction of DE. So what is DE? So DE is the chain of electric field. So so we would know that A, the direction of chain in electric field is upward or point up. Okay, and in the same way in figure B, so the direction of B is clockwise, so I will be downward. So direction of I will be downward. Okay, therefore in figure B, the direction of the chain in electric field is downward. And if we consider in each choices, if E is decreasing, I will give the initial is EI, is the initial, EF is the final electric field. So if E is decreasing, EI should be this thing. So the chain of E will be this direction, or DE. But if E is increasing, from the question they say that E is downward. If E is decreasing, the chain in DE will be downward. And if we look at the figure B, when E is increasing, DE will point up, but when E is decreasing, DE will point down. So as you can see, if A, we want the direction of the chain in electric field upward, we would choose decreasing. And in the same way, in the figure B, if we want the direction of chain in electric field is downward, we would choose E in decreasing also. So therefore, we will choose 2. Next is number 7. So the capacitor plates have an area and separation 2 mm. The plates are in the vacuum, and the charging current IC can have a constant value of 1.8 milliampere, and the charge on the plate is 0 when t is equal to 0. So from this figure, we would know that ID would be in this direction. Okay. And the first question is calculate the charge, or Q. The electric field between the plate, or E, and the potential difference between the plates. So it's the delta V or V when t is equal to 0.5 millisecond. Yeah, first of all, in letter A, you know that I is equal to dq by dt. And we want to find the q, right? So we need to integrate. So dq is equal to I dt using integral form. So in the initial condition, they say that q when t is equal to 0 equal to 0. So q is equal to 0, t equal to 0. And qt is equal to 0.5, t equal to 0.5. So we will get qt is equal to 0.5 minus 0 equal to I times 0.5 times 10 to the power of negative 3 minus 0. And from the questions, they say that IC is equal to 1.8 milliampere. So 1.8 times 10 to the power of negative 3 times 0.5 times 2. It would get 9 times 10 to the power of negative 7 coulomb. Okay. Next, we want to find the electric field, and I think we need to use the Gauss law. So from the Gauss, E dA is equal to Q over epsilon 0. And the question said it have area, but they didn't say the value of that. But we know the radius, so I think we can calculate E times pi r square equal to Q, and Q we get 9 times 10 to the power of negative 7 over 8.85 times 10 to the power of negative 12. And we will get E is equal to around 1.02 times 10 to the power of 5 over pi r square, or it's equal to over area. Okay. And the last thing that we need to calculate in this section, so delta V, and we know that delta V is equal to ED. Yeah, and we know 1.02 times 10 to the power 5 over pi r square times d is equal to 0.00 millimeter. Okay, so we would get around 2.04 times 10 to the power of 2 over area. Yeah, volt, and this is volt over meter. Okay, next is to find dE by dt, rate of friction of electric field between the plates, and does dE by dt vary in time? So first of all, dE by dt is equal to d by dt. So E is equal to like E times A is equal to Q over epsilon 0, so E is equal to Q over epsilon A. So Q over epsilon A, and epsilon 0 and A, I know that it should be constant, dq by dt, and we also know that dq by dt is equal to I, and I is also constant, so we will get constant value. Yeah, but I will calculate it first. So it will be equal to 1.8, sorry, it will equal to 1 over epsilon A times I, and I is equal to 1.8 times 10 to the power of negative 3 over 8.85 times 10 to the power of negative 12, and times 1 over pi r square. So this is the dE by dt, which is constant. And doesn't vary in time. And the last section, C. Calculate the displacement current density between the plate JD, and from this, the total displacement current ID. How do IC and ID compare? So first of all, you need to know the formula of ID, or the current of the displacement. ID is equal to epsilon times the flux by dt. And the flux by dt we can change to the EA by dt. And we know that A is constant, and we will get this thing. And also we know that the E by dt is constant, but you can change the form of the E by dt. So the E by dt is equal to dq d by dt is equal to epsilon A, and we have epsilon A in the front, and epsilon A is constant, so therefore we will get dq by dt, or I. So we would know that ID is equal to IC and equal to 1.8 milliampere, because IC, the equation gives us the value of IC, so it's 1.8 milliampere. So in this section, IC equal to ID. How do IC and ID compare? So IC is equal to ID equal to 1.8 milliampere. So this is the end of the question 7. Bye bye.
Okay, so let's move to the problem 10. So the problem 10 is to find the dielectric constant for the dielectric. So it gives us that there is a dielectric, and the electric flux has this formula depending on T, and they give T, and they also give the displacement current. So that's great. So the displacement current equal to the epsilon, or the permittivity of free space, times the change in the electric flux. Okay, and the displacement current is equal to 12.9 picoampere, sorry. And the change in magnetic flux, so this one, that's the problem give us, and we just use the simple calculus. Sorry, we just use the simple calculus. So the dt to the power of 4 by dt equal to 4 times t to the power of 3, and because the t is equal to 26.1 millisecond, this one, so we have all the numerical value and one constant of the permittivity of free space, so we can find this epsilon, and we find that this epsilon is equal to 2.07 times 10 to the power of minus 11. But importantly, so the because it is the dielectric, right, so we have to involve the dielectric constant. So dielectric constant is basically equal to the absolute permittivity of free space, this one as we find it, divided by the vacuum permittivity of free space, or this one, as we have long known before that the vacuum permittivity of free space equal to 8.85 times 10 to the power of minus 12, this one. So we can calculate the dielectric constant, and it equal to 2.34, here this one. So basically, this problem we use a principle of a formula of the displacement current, and then we just use the simple calculus to find the absolute permittivity of free space, or epsilon, and then we find the dielectric constant by using both absolute permittivity of free space over the vacuum permittivity of free space, and we get the answer. Thank you. Okay, so let's move to the problem